Hello and welcome to Velocity versus Time Graphs. So far in this unit, we've pretty much confined ourselves to looking at graphs of position versus time when we're looking at our constant velocity motion. And we've seen graphs that look much like this, diagonal linear graphs. What kind of motion does that represent? Well, I'm going to show you that down here with a little walker guy. You'll notice that 0 is over here to the left end of our little place where our surface here, where our walker is going to be. So if we look at the y-intercept of this graph of position versus time, it's a 0 y-intercept. Well, remember, we defined the initial position to be the y-intercept. It's the position at time 0. So that means my little walker is going to start at position 0. Then since the graph slopes upward and it's constant, my little walker guy is going to walk to the right with a constant velocity. Watch it again. Here's the motion that would make that graph. Now, looking at our position time graph, there's a couple of things we can tell about the velocity that our man has. We can tell that his velocity is positive and that his velocity is constant. And we can tell that because we've defined the velocity to be on a position time graph, the slope. And this graph has a positive constant slope. It's linear. So a positive constant slope on a graph of position versus time means that you have a positive constant velocity. So if we were going to graph that velocity as a function of time, and notice it's a similar looking graph, it kind of shares a time axis, but we're going to graph velocity now on the vertical axis. To keep it positive, we have to be above the time axis. And to make it constant, so that at any time t it's the same velocity, hopefully you can see that that would be a horizontal line. So a horizontal line above the time axis means that the value is constant and it's a velocity, and above the time axis means it's positive. So let's put this all together, and you can see his motion along with both a position time graph and a velocity versus time graph. Second example, what if the position time graph of the motion was this? You'll notice, by the way, that down where my little walker is going to be, I've now put 0 right in the middle, right, of this thing, right in the middle of his path. So his y-intercept is positive. It's above the time axis. And in real life, that means he's going to start to the right of 0. So here's my little walker guy. Now this time the slope, which is the velocity, it's negative. That means he's going to walk to the left. And it's linear, so constant. So here's his motion along with the position time graph. One of the nice points to look at is, where is it on the graph where he passes 0 in real life? That's right when he hits the time axis. Time axis is position 0, if you were to put numbers on here. So one more time, watch that. So as we talked about a moment ago, we can say several things about the velocity that you can see on this graph. It's negative and it's constant. And how do we know that? Because again, the velocity is the slope of a graph of position versus time. And this slope is negative and constant. On a graph of velocity versus time then, a negative constant velocity would again be a horizontal line, but this time below the time axis, which is negative. So watch all of this together. Again, one of the things to notice is, notice here that when he crosses 0, he still has a velocity. He doesn't stop at 0. Right? So while his position is 0, his velocity is still the negative constant velocity. Now, one other little thing here. What if instead of the graph we had originally for position time, what if that was the graph? What would the velocity time graph look like if that was the position time graph? Well, since we just defined the velocity to be the slope of a graph of position versus time, look at this line. It's parallel to our original one. Therefore, it has the exact same negative constant velocity. And therefore, it would have the exact same velocity time graph. The only thing that would be different about the motion is where he started from. Since it's a greater y-intercept, he'd start further to the right. But his velocity would be the same. What about if this was his position time graph? Well, again, this line is parallel to our original line, therefore it has the same slope, and therefore it has the exact same velocity. So this would still be the graph of velocity versus time for this motion. And the only thing that would be different is he would start at 0. So notice on a velocity time graph, you can tell what direction he's moving, you can tell how fast he's moving, but you can't tell where he starts from. So if I were to give you a velocity time graph to start with, I would also have to tell you where to start your motion in order for you to be able to create a single position time graph. It's kind of an interesting little thing there. We can graph velocity versus time, but we do lose a little piece of information, namely where the object starts from, its initial position. Let's take a look at a third example now. This one's going to be really numerical and kind of full. And you're going to notice here that we have kind of 3 segments to our position time graph. And that means we have 3 different motions going on, one after the other. But they're still all linear graphs. They're all linear segments, and therefore the velocities are constant. It's just 3 different constant velocities. So let's talk about the motion. Here he starts at position 0. Right, so the y-intercept is still 0, so there he is. I've moved 0 over here this time. And then notice he walks away from 0. He has a positive constant slope for 1, 2, 3, 4 seconds. And technically he would get to 8 meters away from where he started. Then look at the slope of the second part. Okay, for 1, 2, 3 seconds, the slope is 0. And that means the velocity is 0. Notice the position doesn't change. And therefore he's just going to stand still for 3 seconds. Then for the last 1, 2 seconds, he's going backwards. He now has a negative slope, or he's moving to the left. But this slope is a little different in a couple of ways. First of all, it's steeper than the original, which means he'll go back faster than he started. And it ends at a position of 2. So he's not going to get all the way back to where he started. So let's match the motion now with the graph. So there's his positive constant velocity for 4 seconds, then he stops for 3 seconds, and then he moves back to the left faster. And notice he ends up 2 meters to the right of where he started. Let's watch that one more time. It's a little more complex. So again, yes, the velocity is changing, but it's still 3 constant velocities, so we can still handle it in here. Let's now make the corresponding velocity time graph. Now to do that, we're going to have to use real numbers this time, since we have numbers up here. We have 3 different velocities, okay? But each velocity is the slope of that segment. And you find a slope by doing rise over run. So let's find the velocity that goes on for the first 4 seconds by doing the rise of the first segment, which starts at 0 and ends at 8. So the rise is 8 meters, right here. And the run is 1, 2, 3, 4 seconds. So his velocity during that time? 2 meters every second. So where would that be on a graph of velocity versus time? Well, you would draw it right at 2 meters per second. And since it's constant for 4 seconds, it would be a horizontal line at 2. Now, for the next 3 seconds, as we talked about earlier, there is no slope. It's 0 over 3 seconds. That means there is no velocity. Well, where is 0 velocity on here? Velocity is on the vertical axis. So 0 velocity is on the time axis. Okay? But he doesn't start, or he doesn't stop, till 4 seconds. So we don't stop until 4 seconds. So notice it's now right on the axis. Now, why this little dotted line in between? Technically, in math language, we have a discontinuity in our function. We have a sharp corner here. Now, this is not realistic. You can't be moving and instantly stop. In real life, this graph would have to have a little curve so that he could slow down to a stop. But we're trying to keep things simple here. So we're going to move from one velocity immediately to another. And when you do that in a function, you connect them with dotted lines. So it's still kind of moving from left to right. But then here we have this little discontinuity. So we're jumping right from 2 meters per second to 0 meters per second. Now, for the last 2 seconds, what's happening? Well, let's do the rise over the run again. Now, be careful. This rise is down 6 meters. Therefore, it is a negative 6 meters. That's where the negative slope comes in. And it's a run of 2 seconds. So his velocity is negative 3 meters per second. Notice, as we predicted, faster than his original velocity. So where's negative 3? Well, that's all the way down here. And again, this occurs from 7 to 9 seconds. So we go from 7 to 9. Again, a little dotted line because of our discontinuity. So if we put it all together here, here's the motion and the position time and velocity time graphs. Touch that one again. This is about as complex as we get in this unit. If you can wrap your brain under and understand the meaning of these graphs and how they relate to the real motion, it's about as complex as it gets in this unit. Okay, hope you enjoyed learning about velocity time graphs.